And we're going to check a little bit. We're going to check a little bit of the homework strategy. Okay. And here's a nice little poster from Will Rogers quotations. Uh, Shai, do you have a time for SI review for exam 3? Okay. Tuesday, Shai will, it'll probably be Tuesday, right? Tuesday supper time, probably look to have another SI review. So that means that over here, there'll be a regular Monday and there'll be a regular Tuesday, I guess, right? Okay, or it might be a longer, starting at 5 and going till 7. Where were you last time? In this building? Okay. It might be in this building. Sometimes they schedule her SI reviews in the ballroom over in the student union. So, but we'll try to have that um, figured out, or Shai will try to have that figured out by Tuesday. I want to talk about the SSG procedures. They're coming up. We're trying to get organized for that. Special study group leaders, most of you have handed back your papers, and that's great. A couple of you still have a paper to hand in. Um, I want to talk about the schedule page. The schedule page is almost ready. And what I would like for you to do is to go in there and look it over and see which special study group fits your schedule. All right, so for instance, if you can't study until after 7 on Wednesday, then look for a special study group that meets Wednesday after 7, and hopefully there'll be a few, et cetera, et cetera. And item 2B here says, be ready to spring, and that means be ready to spring like a tiger. Just spring fast and quick and get a spot, because the students that are going to have first dibs, they'll get first shot, and if they want one, they'll be able to get one. But the rest of you guys that don't have a C, below a C average on the midterms, you're going to have to wait until the second opening, and in that case, it's going to, when I open that up to everybody, it is going to be very, very, very fast. Things are going to fill up ASAP. So you got to be ready to click. And a couple semesters ago, we had a guy, Dr. B, I really need to get into SSG. So and we were starting the signups at 7. And so he was telling me, yeah, I logged in at 6:55, and like every 15 seconds, I kept refreshing my page to make sure he didn't miss. Because what I'll do is I'll make the link to the signups page visible at a certain time. I'll activate that link, and you're going to have to be ready for it. And there's no promises made, no promises intended, and I want you to infer no promises. If you can't get into SSG, it's just one of those things. I know you're not going to be happy if you don't. I wish I had more spots. Get in if you can, and if you can't, that's all right. You're just going to have to try it again for the final. All right, here's what the special study group schedule page looks like. Right now, actually at about 6 this morning, there's still a few things that are not filled in, like Alicia's stuff. I guess, Alicia, I don't know where you are, but her identifying features and where to meet up and stuff at the library, she has to fill in. There's mugshots there, of course. And here's a bunch more. And yeah, so Rebecca Moore has a few more items to fill in. And actually, we've got the specs up here. We'll be filling these out later tonight. Logan, Ashley, etc. But down here at the bottom, Haley's got all her stuff in there. So it's just, but I'll be trying to fill in this stuff in the next 48 hours, certainly by Monday night. Monday night is when we'll start. Here's Caitlin and a bunch of other people. Jonathan is complete. I guess, Jonathan, you're completely squared away. And yeah, question? No, I'm just saying, Jonathan's right. And another thing I want to point out to you, here's Nicole down here towards the bottom. We're going to have more SSG leaders announced because when I had this schedule page updated this morning at about 6, we still hadn't had responses, but we now have a big thick pile of papers from responses, so we'll be filling this page in a little bit more. And by the way, both Caroline and Darian have been special study group leaders. So you SSG leaders or anybody else, if you want to go to Darian's office hours tomorrow at 1 p.m. in the physics, or at noon at the physics building, you can actually, that's a good study session right there. I mean, she's the best SSG leader. She and Caroline are are the best that we've got. And so, anyways, and Caroline's got office hours 1 o'clock, no, 5 o'clock on Monday. So if you don't get into a special study group, or you don't want to, and you want to let somebody else get a spot, go to Caroline's or Darian's, and you can get coordinated with them. And if you have questions about how you special study group leaders, Karina and everybody else, Jonathan, if you have questions about how to prepare, what you should do, ask these two guys. Send them a message in web courses through the inbox, and that'll work really good. All right, now here's the sign-ups procedure. You might want to write this down. We're going to start it Monday night, and hopefully most of the schedule will be visible by tomorrow night, so you have all weekend to look it over and kind of map out your schedule and whatnot. At 7 p.m. Sunday night, okay, so you're getting ready to get back into the swing of things. You're doing homework for next week, okay? 7 p.m. Monday night, starting at 7 p.m. The first group, now this is students that I will identify and communicate with over the weekend to let you know that you'll have the first dibs on joining a special study group at 7. All right, you'll be the only ones that can look at it and eyeball and actually link through to the sign-ups page. All right, at 7. Everybody else will have to wait. And then at 10 o'clock, I'll make the link through to the sign-ups page visible for everyone. And when that happens, you will be able to go in there. So if you have like a C plus average, like a 72% average on exams, you won't be in the first study group or the first group to sign up at 7. You'll have to go in there at 10. Right now, the number of special study group leaders we have and the number of students below 60% exam average is such that there should be, even if all of them take a spot in special study groups, there'll still be a bunch of seats left at 10. So, but it's not going to be enough for everybody. So at 10, there's going to be maybe a couple dozen seats or spots in the different special study groups. And hopefully one of those spots will be in a group that you've already identified as the one you want to participate in, and you'll be able to jump in and click in and join it. And if not, we'll try it again to get ready for the final exam. And we'll do all this again, a different set of meeting times, locations, and a completely different sign up. So if you sign up for Caitlin Widener study group going into exam 3, you can switch over to Karina Tui for the final if you want, if Karina's session is more conducive to your schedule. So there's a lot of flexibility. And my final admonition to you is for those of you that have to wait until 10, please respect that 7 o'clock to 10 o'clock opening period. And make sure that you don't try to jam in there and join. There's probably a way to sneak in, but I'll be watching. I'm everywhere. And so if I catch you trying to do that, I'll eject you, right? And you don't want to be ejected. All right, so questions about special study groups? Raymond, what are you going to do? Did you turn in your stuff yet? Okay. Can you meet with these two guys after class? We'll probably be dismissing a little early today. All right, good. All right, let's keep going. All right, thanks, you guys. Okay, let's double check the Greenland strategy. I have a very simple word message for you, and that is click the link here on the home page, and that'll direct you through to the recording of the session of online office hours. I had to stay off campus yesterday for unforeseen circumstances, and so I had to do the online Adobe Connect office hours. We recorded it, and the diagrams are kind of, awkward. They're not the best diagrams, but hopefully they'll be comprehensible to you. And so if the Greenland strategy, I don't know, we definitely talked through the Greenland strategy, and that one basically is heat, melt, heat, and then heat all the way to the boiling point, boil, and then heat the steam. So the Greenland was heat, melt, heat, boil, heat again. So you have five different cues to figure out on that one. 2 phase transitions and some heating on either side of each phase transition. So total of 5 cues, and it's water. And you had the specific heats for that. Now number 9, and I don't have a note in the PowerPoint this morning for you about number 9. That was the paraffin wax problem. The paraffin wax problem is basically a heat melt heat, similar to the water-based heat melt heat, but with paraffin wax. So paraffin wax has a different melting point. The solid paraffin wax has a different specific heat than solid water. The liquid paraffin has a different specific heat than liquid water. And then liquid paraffin also has a different boiling point, but you didn't have to do boiling, you just had to do heat, melt, heat. So you have 3 calculations, 3 Qs to do, but with different specific heats, different delta Ts, and a different mass, of course. I think everybody had 454 grams. But anyways, that's what you've got to do, right? So it's just like a heat, melt, heat. So the same philosophy, same basic strategy, but different material, and therefore different specific heats and latent heat of fusion. Okay, for the latent heat of fusion, for paraffin, it's 44 calories per gram, versus for water, it's 80 calories per gram. So liquid paraffin, once you get it to its melting point, is easier gram for gram to melt than solid H2O is at its melting point. Okay, so because it's a different material, completely different molecule, much bigger, and different substances have different properties. Question. Okay, the question up front was, I was confused. How do you get it back to the solid? That is a confusion on your part, understandable, but I did have the phrase before pouring it out. Okay, so all you really had to do was heat, melt, heat, stop. I didn't expect you to pour it out and then re-solidify it. Because if I had done that, then the total heat budget would be zero. Because every Q that you do going back to 327 initial temperature is negative of the Qs that you did on the way up. So all you had to do was heat, melt, heat on the way up and stop. All right, so that's why. All right. Okay, expect to see some variety of heat, melt, heat in your future. Maybe even a heat, melt, heat with copper, or a heat, melt, boil, heat with water, paraffin, alcohol, copper. Be ready. Expect the unexpected. All right, now, actually, this is not number 8, it's number 10, I believe. Is that right? Yeah, so this should be number 10, sorry. Number 10 is the battery problem and the spring force. It's actually fairly simple, but maybe a little bit tricky to think your way through. Let's think through. Let's do the strategy and then the calculation. And for this instance, the stretch was given 0.12 meters. So you might have had 0.06 meters for your stretch. Anyways, that pulls the rope back in this diagram to the left. So it's pulling the rope back to the left. Delta X is a positive outward stretch to the right. So your 0.12 meters to the positive, that means your force is pulling back to the negative. That's the minus sign in the force law. And then the pulley changes that negative leftward force to an upward pull force through the rope connected to the battery. All right? And then the battery has a downward weight force, W equals mg. I told you we're not going to ever stop talking about weight force, and here's another example of it. Okay, and it's pretty easy to calculate the weight force. It's just 25 kilograms times good old 9.8 meters per second squared. Here's the two forces that you have to balance. F equals minus kx. So a leftward pull force on the spring has to be the same size as the rightward pull force on the rope up here on the tabletop, which is the same as the downward pull force on the rope on this side of the diagram by the battery. So those two things have to balance. And here's the way that they balance. Okay, so here's let me get my cursor here. Here's my spring force, F equals minus kx. So for us, that's a leftward force. And mg is going to be a rightward force up on top of the table anyways. And that's 245 newtons. All right. So that battery pulls downward. The Earth pulls that battery downward with a 245 Newton downward force. And then on the other side of the pulley, Courtney, it's pulling rightward with 245 Newtons. Okay, and the spring is pulling back with the same number of Newtons because they're all balanced. It's all steady. It balances at 0.12 meters. So basically, this is the formula here, mg equals kx, that you have to figure out. And the minus sign is if you do the calculations carefully, we kind of skipped over some steps, but if you do them carefully, the minus signs cancel. All right? And basically, you're down here to a quotient 245 newtons divided by 0.12. All right, and that gives you the spring constant K, which in this case works out to 2,042 newtons per meter. And a newton per meter is, let's see, that's a kilogram per second squared. That's interesting. Question? The only time the negative sign matters is when you're trying to balance, when you're trying to draw diagrams, either horizontal or vertical, and only vertical. Horizontal and only horizontal. But in this one, you kind of have to figure out, you have to use your horse sense to figure out, okay, what the spring force resists with is what the battery pulls down with. And if you can get that common sense conclusion, then you can just do a straight plug-in. 245 equals K, because the minus sign doesn't really affect the size of the pole, only the direction. Right? So if you know that your pole, your KX has to give you 245 newtons, you're on easy street. All right? Another question on this. Yes? 245 mg, that's the weight force. 25 times 9.8. Okay. 25 kilograms times 9.8 meters per second squared. Another question. All right, let's keep going. I wanted to do this calculation with you last time, but we didn't quite have enough time. The electromagnetic wave equation, C equals lambda F, this is just a version of the generic wave equation, V equals lambda F. C being the speed of light, the customary symbol. I don't know who started using it first, but anyways, that's the one we use, C for the speed of light. And Einstein's famous equation, E equals mc squared, yeah, that's the mass of an object times c squared, the speed of light quantity squared, which we talked about. It's 3 times 10 to the 8 meters per second. Now, in this kind of a calculation, either figuring out a wavelength or a frequency, you're going to have to be really careful either with your calculator or with scientific notation if you're doing it on pencil and paper. And so let's try to work through that. Now, the wavelength is a spatial measurement. You know, peak to peak if it's ocean waves, or trough to trough, you know, for the deep part of the wave to the deep part of the next wave. For electromagnetic radiation, it's a peak in the intensity of the electromagnetic field. And those peak, the electromagnetic field goes from peak to 0 to peak, you know, in the distance of one wavelength. Period is a temporal measurement. That's the distance in time. So many seconds, so many milliseconds, so many nanoseconds from one peak to the next. And the frequency is the inverse of that. All right? And so what we're going to do is use this now and calculate the frequency for a red color, 656 nanometers. Okay, so that means we're going to start with a wavelength, which is relatively easy to measure in the laboratory if you do a little bit of trig and you have a good diffraction grating, for which you know the spacing of the diffraction grating. Anyways, we're going to take the electromagnetic wave equation, C equals lambda F, and to get the frequency, we're going to modify it just a little bit. We're going to divide both sides by lambda. All right, so we're going to park this lambda in C equals lambda F. We're going to divide both sides and park it over here under the C. All right, so these two equations are equivalent. And this one on the right allows me to figure out the frequency. Now, if you want to figure out in another problem what the wavelength is, given a frequency, this is the one that you would use. So this one would allow you to figure out the wavelength. C over frequency equals wavelength lambda. Right? So either one of these is kosher, and they're all based on this classic expression. This is the way, when a physicist talks about the wave equation, they're usually talking about this one right here. Courtney, did you have a question? Or are you just kind of going like this? All right. Just faking me out from the back row? All right. So let's work on this. All right. So we're doing 656 nanometers. Now, a nanometer is 10 to the minus 9 meters. A nano, that means a billionth. B bravo, billionth. The billionth part of a meter. And we've got 656 of them. So down here below, in scientific notation, it's this way. And you may say to yourself, hey, Dr. B, why are you even bothering with scientific notation? Well, I'm not going to accuse anyone in here that's a student this semester of being a slacker. But sometimes you forget your calculator for the exam, and you got to do a calculation like this on paper. This is how you do it. You set it up this way. Here's the speed of light, 3 times 10 to the 8 meters per second, up on top. That all looks copacetic. And that's going to be my frequency, that quotient. Now, what I normally do is I try to get all my scientific notation exponents into one bindle in the numerator. And the reason that you can do that is because 10 to the minus 9 in the denominator is the same as 10 to the regular 9 in the numerator. So you already have 10 to the 8 in the numerator. 10 to the 9 in the numerator, John, is going to give you a total of 10 to the 17 in the numerator. Okay? So now, in this one, my denominator now is just 656. All right? And I can punch that in on my calculator. And the numerator is just 3. All right? And I can punch that in on my calculator. And then I got to deal with 10 to the 17 in the calculator. And here's how you do it. Okay? If you're going to do this one on a calculator, this is what you would type in. A 3, and then EE, enter exponent, and then 17. That will give you 3 times 10 to the 17. And then you hit the divide by button, and then and then you key in 656. And then you hit the equal sign. All right? Now, you're going to want to do this in a minute. You better break out your calculator and your clicker, because we're going to do this. Sarah, you have a look on your face of pain. We're just, get your calculator. That'll make you feel better. You'll feel all sparkly and nice. As long as you have a calculator out of some kind or another. Okay, Logan, make sure don't let her, good. Everything's squared away. All right. All right, so 3EE17. Now, your calculator, it might be a little different. I don't know, what's the Mac, the iPhone? You got to turn it sideways. Yeah, on the iPhone, it's EE. Use the EE button, and you can do it on your iPhone. Although, on the test, you can't do it. You can't use your iPhone on a test. Okay, it's in there. Now, if you have a regular calculator that's TI, I think has EE, but if it's some other kind of calculator, it might be a little different. Okay, so you do this on your calculator, and what it tells you is 4.57, and then up in the upper right of the 4.57 is a little number 15. So a little number 14. And so what that means is 4.57 times 10 to the 14. All right, that's how a lot of calculators will show it. All right. And so what you then have to do is express it, and I'm going to show you how to do this in terahertz. Okay, now a terahertz, oh, by the way, per second, that's all that's left in this calculation. 4.57 times 10 to the 14 per second. That means how many waves per second, go past you as this beam of light goes past you. Per second, the other name for that is hertz. The abbreviation for hertz is Hz. So it's not talking about car rental. It's a guy named, I don't know, I think his name was Heinrich Hertz. German guy, first one to measure and observe man-made electromagnetic waves. He created them in a lab, measured them, and verified for the first time what people had only predicted theoretically. Anyways, they named the unit of frequency after Professor Hertz, Hz. So a terahertz is bigger than a megahertz. Megahertz is, or megacycles per second. Megahertz is where FM radio is. FM radio is up in the 90s and in the low hundreds of megahertz of frequency. AM radio is in the hundreds of kilohertz. Like WDBO is ESPN Sport Radio is 580 AM. That's 580,000 cycles per second, 580 kilohertz for the frequency of WDBO AM. And WDBO FM News 96.5 is 96.5 megahertz. And this one is 10 to the 12th. So let's work our way up. 10 to the 3 hertz. Go ahead and make a list of this. It's not in the slide, but it's probably better for you to write this down. Okay, 10 to the 3 hertz. 10 to the 3 is a kilohertz. Little k, capital H, Z. 10 to the 6. Okay, I'm holding up 6 fingers, a full hand and a thumb. 10 to the 6 cycles per second is a megahertz. Capital M, capital H, Z. All right? Now, don't let me cause you to cough your lungs out on this because we're going up another 3. All right? Here we go. 10 to the 9 hertz, 10 to the 9 cycles per second, 10 to the 9 waves per second is a gigahertz, a gig. Capital G, capital H, Z. That's 10 to the 9. Now we got more than that. Your cell phones operate in the gigahertz frequency range, depending on which kind you got. And over in Europe, I think it's slightly different, but I think they're up in the gigahertz over there too. Okay, next one up is 10 to the 12. So 2 hands worth plus another 2. Okay, there, hold up 2 fingers. 2 fingers, yeah. Okay. Okay, so these many. As my son used to say when he was 3, these many. He couldn't count very good. These many. All right, so 10 to the 12 is a terahertz. Capital T, capital H, Z. All right, now, we've got 457 here. All right, because right here, we've got 10 to the 14. So split out 10 to the 2. Okay, 10 to the 2 times 10 to the 12th is 10 to the 14th. So write that down. 10 to the 12th times 10 to the 2 is 10 to the 14th. That's good. And now multiply 10 to the 2 times 4.57. That just moves the decimal point over 2 points, 2 places. All right? So here you go. There's the 10 to the 2 factored into the 4.57, total 457. The capital T here is terahertz. And that's 10 to the 12. Now, here's another way to look at it. Okay? So here it is, 10 to the 14. Now, here's where I factor the 10 to the 2 out. And you're going to have to do this in a few minutes, in about 2 seconds, as soon as we get to the next clicker question. Okay, so factor this, and then put these two babies together. 4.57 and 10 to the second power is 457. All right? And then your leftover is 10 to the 2, and that's a capital T. All right? Now, the reason I'm going through this with you is I want to give you realistic frequencies. You know, like this is the frequency for a very beautiful red diffraction line, the H alpha diffraction line, 656 nanometers. This is the frequency for it. If I give you an FM radio station for homework, you can handle FM. All right? That's going to be 10 to the 6 HZs. So you're going to have to work around with that. Or a cell phone frequency for homework. That's going to be 10 to the 9s somewhere. All right. Now, questions about this before we continue, because you're going to have to do this now on clicker. Yes, Amber.
Why do you factor out 10 to the 2?
Because I'm going to ask you for the number of terahertz. And so you want a number times 10 to the 12. I mean, if we were doing okay, and Amber's asking a good question. Why do I ask for terahertz? If we were doing written exams and I was eyeballing everybody's paper, you could stop right here. Ding! That's perfect. That's right. That's on the money. But with clickers, I don't like to do scientific notation on the iClickers. Okay? So I want to ask you for the numeric part, either a 4.57 or a 457 or some other number. And so I have to be able to say, give me the full number of megahertz, or give me the full number of terahertz, or whatever the frequency happens to be. Also, if I was going to give you or ask you a wavelength, I might ask you how many nanometers. And you say, well, for a red light, it's about 700 nanometers. So you type in 700. This one, your nanometer is 656 nanometers. So I wouldn't ask you to type in the letter NM. And I wouldn't ask you to type in the letter THZ, but just the number part. And so that's why we're trying to isolate a convenient bindle of numbers without a decimal point, if possible, because decimal points on the iClicker system are a pain in the, you know what. All right, so let's try another calculation. Courtney. 10 to the third is kilohertz. Okay, 10 to the third is kilo, whatever it is, kilometer, kilohertz. Okay, 1,000. So lowercase k, capital H, Z for kilohertz. All right, clicker question time at the OK Corral. And this is going to be a calculation. Type in, Amber, type in your answer to the nearest number of terahertz. Okay, nearest whole number. Okay, just like we just went through. Right now, this is another beautiful line from hydrogen. This is H beta. And we saw that in lecture, the beautiful kind of tealish, aqua-ish color. And this image that you're looking at is from a Physical Science 1121 lecture over in the old physics building in the deep, dark dungeon, room 260, the subterranean cave. Now, let me turn the lights on for you. And hopefully you can. So take a few minutes. And definitely kibitz with your neighbors. Raymond, don't forget to talk with Caroline after class. Caroline. Raymond, hold your hand up and keep it up. That's Raymond over there. He's going to give you his specs. Did you guys type in that other stuff? Great, thank you. You guys are awesome. What can I say? Anna Smith. Calculating okay? Good.
I'm not. My job to figure out.
Well, you got these two guys to keep you on the straight and narrow. One on the left, one on the right. No messing around. Plus, Megan's over there supervising everybody, keeping an eye on everybody. That's good.
I haven't even I'm trying to figure out how to plug everything in right.
486 times 10 to the minus 9 in the denominator. Yeah.
Oh. Okay. What happened to the 3 Oh, divided by
Yeah.
186.
I'm setting it up like this, but I don't know what
Yeah,
to put.
it's 10 to the minus 9. It's a
Oh.
it's a nanometer. So a nanometer is always, the number of them times 10 to the minus 9.
Okay.
So that's what, let's see on your previous page.
Yeah.
Yeah, so this was 656 nanometers.
Mm-hmm.
So you express it 656 times 10 to the minus 9. Same thing over here, 46 times 10 to the minus 9.
All
Okay.
right.
Thanks for this notebook paper.
Oh yeah. Stop. It's okay. Either side. Or no. So yeah, I could have been one. Yeah.
How about this?
Nice.
A picture of Galileo. Forsooth. All right. Okay, 30 seconds. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got going here. What? Sick. Wait a minute. Is Wait a minute. Let me get out my calculator here. Let me just. We're going to the document cam. I better verify this. Let's get this. Okay, I'm going to keep going with the podcast, but I'm switching over the document cam because I want to go over this calculation. All right. Oh, you can't see it. All right, see if we can do this. All right. 3EE8. Oh, wait a minute. Yeah, but I'm going to use scientific notation the entire way. Let's see. Divided by. See, here's how you do it if you want to do scientific notation the whole way. 486 EE 9, change the sign, equals. Okay, 617. Whoa, look at that. But you can see the answer there. I wonder if I can make this bigger. Let's see. All right, so there's the answer. Now look at that. 284, 617, 950. Okay, so 3, 6, 9, 12. So 617 times 10 to the 12, 617 terahertz. And apparently 94% of you got that right. So you guys are geniuses. Good. I'm glad about that. So that means for extra safety, I'm going to trot you through some frequency and some wavelength calculations for homework. All right, I want to talk about pendulums and phase diagrams. Now, there's a story that our favorite scientist, Galileo Galilei, was at church one day in Pisa, and he was just sitting there thinking about cannoli or something, or whatever he was thinking about. And he looked up and he saw a big lamp. Now, in those days, they didn't have nice fluorescent lights like what we had. And so what they had was like chandeliers, and a lot of them, but not fancy chandeliers, just chandeliers with lots of candles on them. All right? And he was able to watch one of, and what they'd have to do is they'd have to lower them by ropes. So they'd lower them away, stock it up with fresh candles at the beginning of the day, and then hoist it back up. As you hoist it back up, and you tie it off and stabilize it up there where it lights up the whole room, it's going to maybe sway a little bit. And so what Galileo found was that he being a scientific, almost like a nerd he decided to use his heartbeat to time it. And it was a really long rope, and it would swing, And he probably said to himself, forsooth, that thing is periodic. It has the same amount of time left to right as it has right to left. And so he was able to use his heartbeat to time it and verify that, yeah, it does, within plus or minus a heartbeat or two, it's periodic. It repeats itself. Now here's a diagram of that. Can you move over a little bit so I can use this? Here's a diagram of Galileo. And most of the pictures of him, he's got a really good beard and a lot of hair. So I made him look kind of like the wild man of Borneo there. But he's observing a pendulum of length L. And what I'm going to show you is that the oscillation frequency that he could have measured if he was thinking, he probably wasn't thinking about frequency, he's probably just thinking about time and distance. It depends on two things, the length and good old G. At leftmost X position, it stops. That's the turning point of the motion. Okay? And at rightmost X, over here, so this is, right here is rightmost X over here. Let me spell this out. It also stops, and that's another turning point in the motion. At the bottom, the center of the motion, the velocity is maximum. I hope that appeals to you. If this angle up here, let's call this angle alpha, okay? If that angle is pretty small, then you have a very regular oscillation. And it oscillates because on this string, or rope, in the case of Galileo probably, it actually loses altitude as it goes from leftmost to center. So here's the center of the motion right down here. So there's the center of the motion. And from leftmost turning point to the center of motion, it's losing altitude or gaining altitude if it's going from the center out to the leftmost turning point. And so as a result, this is a symmetry point, and the velocity is a max. Kinetic energy is a max. And gravitational potential energy is a min. Okay? Also, momentum is max at x equals 0. Now that's important for us because for this simple system, you can draw a very, very lovely phase diagram. And let me spend just a few minutes sketching a phase diagram for you. We're doing this for a simple pendulum, and actually a diagram like this, when applied to the atom, will explain the periodic table. So this is a natural point to introduce a phase diagram. Write a horizontal and a vertical pair of axes. We'll call this horizontal axis the x-axis. All right, so this would be like the position of the shadow. I mean, if it had light, sunlight shining down on this thing, that would be this position here. All right, so here's the x-axis down there. You can think of it that way. Okay, and put a dot or put a line here for rightmost. Sure. So here's rightmost. It's a positive number of x. So like 7.3 meter. No, that's too big. 0.23 meters positive. And then over here, same distance, try to eyeball it in the leftmost point out here. And try to make these symmetric, left and right. Now, the vertical axis is momentum. And on this one, we're going to use rightward momentum for positive and leftward momentum for negative. Okay, so make a note off to the side. Okay, and I'll put a little arrow up here. All right, now, maximum momentum occurs at the center of motion. Okay, so this and this occur at x equals 0. Right? So maximum momentum, max kinetic energy, and min gravitational potential energy. So go up a couple lines of graph paper and put a horizontal. And this is largest rightward momentum. Okay, up there. And William de Klerk, that happens at x equals 0. When it's down at the bottom of its swing, that's when it's got the most momentum, either rightward or leftward. So because it has equal leftward and rightward, let's do a horizontal line, the same number of lines down here, and we'll call this largest leftward momentum. Okay, right down there, i.e. negative. Okay, now let's figure out the intermediate points. These are 4 points in the motion. We have a turning point, leftmost, turning point, rightmost. We have the symmetry point, and it goes through the symmetry point repeatedly. It's periodic. So let's trace out and figure, let's start at the rightmost. If you're out to the right and you let this thing go, it's going to move to the left. Right? So if you start here, it's going to move left. That means you have to have leftward momentum. Sketch in a very graceful curve right here so that it starts flat here. And boy, I'm going to do pencil with the rest of mine. Hopefully you can read it. All right. Now once it's on its way left, it started here. Go ahead and write in t equals 0 over here. Okay. And then it keeps going. It goes past that symmetry point, and it goes out to the leftmost. It goes out to here. It goes out to the leftmost turning point. Okay, so that's a similar curve, and I'm going to do this a little bit more graceful. Yeah, that's better. Okay, this should be straight up and down here on the right and perfectly flat over here. The motion is symmetric on the way back. If you start out here on the leftmost side and you let it go, you're heading back to the right. So now you have momentum up here, and then you overshoot and you get all the way down. Yeah, that's not very good. There we go. My wonderful students, this is in general an ellipse. And in the free chapter that I gave you a couple weeks ago, this is the very last diagram in the chapter. It is important for us. All periodic motion will have, and this thing is called a phase diagram. Okay, so this is the phase diagram of a pendulum. Write this down. The phase diagram of every periodic system will usually be an ellipse or maybe a circle. Let me repeat that. The phase diagram of every periodic system will be elliptical or possibly circular. My wonderful students, the very last thing is to realize that the area of this ellipse, it's easy to calculate, has units of angular momentum. Did you write that down? The phase diagram has units of area, angular momentum. Planck's constant has units of angular momentum. And that is what we will talk about on Tuesday. You're dismissed. We'll have some homework by lunchtime tomorrow and due on Tuesday. You're dismissed. I'll see you next time. Mr. Ordonez. This is good. Caroline, thank you.